Hello. Now let's talk about variable substitution, our next topic. Follow my cursor. Suppose that g and f are functions such that the image set of f equals the domain of g, and such that f is continuous at x equals c while the limit y goes to f of c of g of y exists. Then the domain of g composed f will be the same as the domain of f as before, and letting y equal f of x, we get the limit x goes to c of g of f of x equals the limit y goes to f of c of g of y. I didn't necessarily promise the continuity of g at f of c. It could be, but it might not necessarily be continuous there. Okay, let's go here. Here's an example. Let y equal 4x. We get the limit x goes to 7 of the sine of 4x equals the limit y goes to 28 of the sine of y, which equals the sine of 28. And now I need to qualify something, guys, where we're letting y equal 4x, and I should have put that there, and I apologize for that. Okay, what we're doing, guys, is we're replacing y with 4x. And as x is going to 7, 4x, which is y, is evidently, it's going to go to 28 because y is 4 times x. And if x is going to 7, y is going toward 4 times 7, which is 28. That's where the 28 comes from, okay? So that's called a variable substitution. We can do that. Now here it probably felt a little silly. You're like, well, Jason, couldn't we just stayed here and just thrown the 7 in? Yeah, sure. That would have been good by composition, but sometimes this substitution, it comes in handy. It's just handy to have. It's just nice. Letting y equals 2x minus 5, that's not very elaborate either. We get the limit as x goes to 5 halves of the sine of 2x minus 5 equals the limit y goes to 0 of the sine of y, and by continuity of sine, well, just like up here, that's the sine of 0, which is 0. Again, and I forgot to qualify where y equals 2x minus 5. Sorry about that. I forgot to qualify. And, oops, I don't want it to skip that space. Excuse me. Well, it's not going to cooperate. So y equals 2x minus 5. Oh, well, I'll have to. But anyway. So what's happening, guys, is x is going toward 5 halves. 2x minus 5 is going to go toward 0, because if you throw 5 halves in here, that's going to make this overall 2x minus 5 vanish, okay? So as x is going to 5 halves, y is going to 0. Notice we went from something that was okay to something that was very pretty, namely this. We very much know how to handle this. And yeah, we can handle this as well, but this is even nicer still. I want you to have that idea of variable substitution at hand. Don't take this lightly. I want you to learn this thing of variable substitution. Okay, let's move on. Now, this is a change of topic, a change of the guard. Now, infinite limits. Now here, we're sort of going to go back in time. You remember with the horizontal asymptote, as x went to either infinity, f of x would go towards some finite number for a horizontal asymptote. Here, these are not horizontal asymptotes, and they're not vertical either. We can't. They're actually neither vertical nor horizontal. These are their own thing. So what if f of x boringly goes to infinity as x goes to some either? What if f of x goes to either positive or negative infinity as x is going toward either positive or negative infinity? Like, suppose f of x is still going just one way, but we have the bad news is we have to take x to infinity in order for f of x to go to infinity. Then you have these type of limits. I could have introduced these probably several videos ago, but oh well. I don't think anything's going to be pedagogically lost. So infinite limits where f of x gets large as x also gets large. These limits are not vertical nor horizontal asymptotes, okay? These limits do not really exist, but they behave in a predictable manner, and we're going to sort of give them a life form here. and assume D is an appropriate domain. Well, actually, I kind of defined D appropriately already, but oh well. Let A be a real number. Let D be a subset of the reals that's a superset of the closed interval A, comma, infinity. Let F be a function from D to R. We say that the limit x goes to plus infinity of f of x equals plus infinity if f of x gets arbitrarily large in the positive sense as x goes off forever to the right, and hence gets arbitrarily large in the positive sense itself. For example, and here this is just an example right here, guys. Excuse me, the limit as x goes to positive infinity of x squared equals positive infinity. That's an example. So as x goes arbitrarily far to the right, y equals x squared is going to go, high up in the sky, and it's going to go up pretty fast at that. But as fast as it goes, you'd have to go forever for it to go, infinitely high up. Unlike the case with the horizontal asymptote, in which case you blew up to infinity at a finite number. Here, that's not happening. Here, you actually have to, as fast as it is, it's not fast enough to ever go to infinity at any finite number. X has to go to infinity for x squared to go to plus infinity. And, and as it turns out, in an analogous fashion, let B be a real, let R be a superset of D as before, which is a superset of negative infinity, comma B. So, now that's sort of the counterpart to this guy. Let F be a function from D to R. We say that the limit as x goes to negative infinity of f of x equals plus infinity if f of x gets arbitrarily large in the positive sense, so we're going up forever in the y direction. As x goes off forever to the left instead of to the right, which was up here. And hence x itself in domain gets arbitrarily large in the negative sense because it goes forever to the left. So as x is going forever to the left, f of x is going up forever. But it's actually going up. It doesn't have to necessarily go up rapidly, but it is in this case. X squared goes up pretty fast. Square root of x would go up forever, but it wouldn't be so rapid. But anyway, we're not doing the square root. We're just doing the square here, okay? So the limit as x goes to negative infinity of, now you got to put parentheses around it because you're squaring the whole negative x. That's an algebra mistake students make. They leave off their parentheses. But that guys goes off to positive infinity, okay? And in an analogous fashion, I go back here to a infinity again. I define f accordingly. Now the limit x goes to plus infinity equals negative infinity if f of x gets arbitrarily large in the negative sense. It's going down forever in the y direction as x goes off forever to the right. And then you can create an analogous scenario where we go down forever as x goes forever to the left. And that's this guy down here where my cursor is. Okay, and so these are analogous. Now we're going to be a little bit liberal and a little bit allowing in that I'm going to use, they're not real numbers, mind you, okay? But I'm going to use the symbols plus infinity and negative infinity. And I'll sometimes denote plus infinity as infinity, as I've talked about before. These elements are not real numbers. We can do some arithmetic with them, but you have to take caution. You can't just do anything your heart desires with these, okay? You got to be a little bit careful. Infinity plus infinity is, we're going to intuitively define it to be what we think it ought to be, which is in positive infinity. And negative infinity plus negative infinity, which is neg infinity minus infinity, we're going to just define it to be that these two to be one and the same, and we're going to define them to be negative infinity. We're going according to our common sense. And positive infinity minus a negative infinity, but commonsensically, it would make sense to define that to be the positive infinity and to define infinity plus infinity to be the same thing, positive infinity. And now here, ask your professor. If I divide by either infinity, the only way I could define it really would be if I could leave it undefined. If you want to leave this third guy undefined, that's okay. Ask your professor. We're not going to dwell on this one very much, but I'm going to define it to be 0. That would be the common sense definition. Again, this is a little liberal and a little bit loose. Don't go throwing this around too much in your calculus class. But I'm doing it for convenience, and it shouldn't pedagogically hurt anything. These are just symbols that allow me some convenience. Infinity times negative infinity, common sense would tell me that's negative infinity. And commutativity is always going to push through here. We're not going to lose commutativity. And positive infinity times positive infinity, and negative infinity times negative infinity, common sense would tell me infinity. So that's the definition we're going to make. These are definitions. As long as r is positive, r times infinity is infinity, and commutativity. R times negative infinity is negative infinity for positive r. For negative r, r times infinity would be negative infinity, and r times negative infinity would be positive infinity. And if r is positive, infinity over r would be plus or minus infinity over r would be plus or minus infinity. That means we keep the same sign. Like positive infinity over pos r would still be pos infinity. Negative infinity over positive r would still be negative infinity. This means we don't change the sign because we're dividing by a positive r. Now, if we divide by negative r, we do change the sign right here. So positive infinity over a negative value of r would give me negative infinity. So pos infinity over r would give me negative infinity. And negative infinity over r would give me positive infinity. Notice I turn these signs around. This is plus or minus. This is minus plus with the minus on top. That means there's a sign change. That's what that means, okay? And of course, common sense would tell me that if infinity plus or minus r would just be infinity, it would be unaffected. Likewise, negative infinity would be unaffected. And if I raise infinity to a positive power, or if I raise infinity, I need to be careful about this one. No, let's just keep that positive infinity. Let's not, let's just stay, that's only true for positive infinity. Sorry guys, I corrected that. So positive infinity raised to a positive power is still positive infinity. We're not going to mess with negative infinity this time. That gets a little dangerous. And positive infinity to the r power would equal 0 if r was negative. And we're not going to, and if r is 0, we're going to leave it undefined. We're not, infinity to the 0 power, 0 to the 0 power, we're going to leave all that undefined, okay? It's dangerous to define those things. It's just not a good idea. So we're going to leave those undefined. We're also not going to mess with infinity minus infinity, infinity divided by infinity, 0 times infinity. Now we still can't do any real number divided by 0. We can't do it because there's no way to decide would it be positive or negative infinity. So we're not going to do it. We're leaving it undefined wisely. And infinity divided by 0, even it we're leaving undefined, okay? The usual rules and conventions are assumed whenever an operation is defined. So associativity and commutativity, we're making our definitions such that we keep associativity, we keep commutativity. We don't want to lose those. That would not be fun, okay? And again, using the above definitions, we have for the appropriately defined functions f and g for each bulleted number. These are just some rules. Limit x goes to c of f of x equal if this limit equals plus or minus infinity, and if the g limit is just a finite real number, then the sum of the limit is the limit of the sums, which is going to be that same infinity that we had. No sign change, same sign. And now again, if the f limit is infinity and the g limit is positive, then the product is going to be the same type of infinity, no sign change. If the f limit is is one type of infinity, either positive or negative infinity, and if the g limit is negative, then the product of the limit is the limit of the product, or the limit of the product is the product of the limit, which is going to be the opposite type of infinity. We do indeed change signs this time because r is negative. And if the f limit is one type is either positive or negative infinity, and if the g limit is a real number, then the limit of the difference is the difference of the limits, which is going to be the opposite sign, because we're subtracting, the infinity is on the tail end of the minus sign. So yeah, we will change signs there. Like r minus infinity would be negative infinity. R minus negative infinity would be positive infinity. So r minus infinity is negative infinity. R minus negative infinity is positive infinity. I think I said that right. That's a tongue twister. It's according to our common sense. R minus infinity is negative infinity. R minus negative infinity is positive infinity. I said it right. Okay. Just making sure. I think I said it right the first time, but I'm just making extra sure. Okay. Number 5, if this limit is either positive or negative infinity. Now, you can't be both at the same time. Now, don't get me wrong here. Like, basically, this is saying you're either equal to one or the other. You can never equal both at the same time. I don't want to give you the wrong idea here. We never have ever been that way, okay, throughout this whole class. You either equal one or you equal the other. You either equal one of them or you equal the other one, okay? That's always true. So if the limit of x goes to c if f of x equals one of the infinities, and if the g limit is the same signed infinity, so if this is positive infinity, this is positive infinity, and if this is negative infinity, this is negative infinity, then the limit of the sum is the sum of the limits, and you get the same type of infinity. Now, if they're opposite, and if you subtract them like this, the limit of the difference is the difference of the limits, and you know what? You get the infinity that went with f, the same sign as f. And then in an analogous fashion, if you put the g on the head end of the minus sign and f on the tail end, you're going to get the g sign, the same infinity that went with g. And if they're both the same sign, then the limit of the product is the product of the limits, and we get positive infinity here. And I'll put my plus sign just to avoid confusion if it will let me. But again, remember, I'm using infinity without any sign to indicate positive infinity. Remember our convention there? I don't want to go back and have to change signs all the time like I had to do just then. But I did it at that time. That's okay. Now, if f and g are opposite infinities, then the limit of the product is the product of the limit, which equals negative infinity. And my time is getting pretty short here. And again, if the f limit is one of the infinities, and if the g limit is a negative number, then the limit of the quotient is a quotient of the limits, which is going to be, again, the opposite sign. So that behaved kind of like multiplication behaved. If the f limit is one of the infinities, and if the g limit is a positive, then the limit of the quotient is a quotient of the limits, which is the same, equal to the infinity that went with f. Whether if f was positive infinity, so was this. If f was negative infinity, so was this. Whereas the opposite was true up here. Number 12, if the f limit is one of the infinities, and if the g limit is just some real number. Now, if we put, this is true. We don't want to ditch this guy. The limit x goes to c of g of x over f of x equals 0. That's going to be handy later. 12 is important. We don't want to go without 12. This is a good guy to have. And you see why earlier I wanted to define a real number over infinity to be 0. That was a little sloppy, but this isn't sloppy. This is a limit right here, guys. And we want this to be true. 12 is important. And then 13, if the limit x goes to c of f of x equals one of the infinities, and if the g limit is a positive real, then this limit will make sense, and the limit of the exponentiation will be the exponent of the limits, which will be the same sign as f. You know what? That's dangerous, though, I think. No, let's forget about that. That's a mistake. Let's just do positive infinity only. Negative infinity could be very strange here. And this would just be positive infinity here. Sorry about that, guys. I need to correct that. It's dangerous to work with negative infinity when we're dealing with exponents. And in an analogous fashion, on 14, if r is negative, then intuitively infinity to the r would be 0. Now we're using positive infinity. I had to make that correction there. I'm only using positive infinity for my f limit. But in analogous fashion, this is going to be 0 and not positive infinity because r is negative. And that will be all for this video. Thank you. Bye-bye.